Today I want to talk about something known as inductance. Last time we had talked about, the last time we met, we had talked about calculating the EMF of a conductor that is being ambayo inapitishwa in a magnetic field. The voltage being induced in that conductor, we are able to calculate it and have a value. So today we are going to talk about inductance, because the things we have been talking about so far in magnetism, and especially electromagnetism, is inductance. And what is inductance? Now, when you pass a conductor that is carrying current in a magnetic field, this you will find that this conductor will have EMF being induced or being produced in that conductor. Now, what happens is that the change in that current flowing in that conductor or in that circuit will oppose. It will oppose the EMF being produced. Now, when that current flows in that conductor or in that circuit, it creates a magnetic field around that conductor. The field of that conductor, the strength of that magnetic field around that conductor will depend on the magnitude, the amount of current flowing through it, and it will follow the changes in that current. So if there is a change in that current, then the magnetic field will also change. Now, when the magnetic field changes, kama kutakuwa na any changes in the magnetic field, what happens is that we have a change. We'll have a change. We'll have an EMF being produced or being induced in that conductor. Sawa. This is generally the phenomenon that we call electromagnetic induction. When you have an EMF being induced in a conductor or in a circuit because there's a change in the magnetic field around that conductor, then we call that electromagnetic induction. Now, that induced EMF, that is in the current or in that conductor, which is created by the change in magnetic field because of the change in current in that conductor, will have an effect of opposing. I think we can see of opposing the change in that current. We had talked about this law, Lenz's law. We had talked about it. The EMF produced in that circuit or in that conductor will oppose the cause, the reason causing it. Now, we find that in components in a circuit, especially motors, they have inductive loads. There is that element of inductance. Because a simple form of an inductor is a coil. Ukipata a conductor and then you have coils, you form coils with that conductor, then that principle of inductance comes about. Now, we have components in circuits that are built for that purpose, na hiyo ni inductor. Components that increase inductors, kama vile tuna resistor, tuna capacitor, kuna inductor ambayo increases inductance in a circuit. Now, this inductor, the amount of inductance that it brings to a circuit will depend on a couple of things. One of them is permeability. We had talked about this component, this term, permeability, as we are talking about when we are beginning this topic. Tukasema permeability is that measure of magnetism that a material obtains when it is exposed to a magnetic field. Are we together? There are so many factors that will affect inductance. Now, we can categorize inductance as self-inductance or mutual inductance. When that change in EMF, when that EMF is produced in that same circuit, if you have a circuit and then the change in current induces an EMF in that circuit, then we call that self-inductance. When you have two circuits, one is adjacent to another. Kuna moja ambayo is adjacent to another, and that change in the induced EMF in one circuit induces EMF in the other circuit, then that we call mutual inductance. Mfano ni transformer. I think we have seen transformers. Do you have an idea how a transformer works? We have one. It's basically a coil. We have a coil wound around a core, and we have primary coils and we have secondary coils. So we'll pass current in the primary coil, then it creates a magnetic field. That magnetic field induces kunakuwa na EMF generated ama produced in that coil. That EMF in that primary coil will then induce EMF in the secondary coil. Hapo ndio sasa tunaongea kuhusu step up or step down. You can induce that EMF in the secondary coil ikuwe higher, or you can induce EMF in that secondary coil ikuwe lower. Kwa mfano katika hizi power lines ambazo tunaziona hapa nje katika nyumba zetu, you will find that voltage is, let's say mfano for 15 volts. But we want ile ambayo tunatumia kwa nyumba ni 240. So you'll find your power ama your voltage induced EMF in that line itaingia katika the primary coil of that transformer. Then we'll find that EMF will induce a lower voltage katika the secondary coil ifike mpaka 240, and that is what we are supplied with in our houses, and that is what we call mutual inductance. Now we can calculate the value of the EMF induced in a coil, and if we were given kwa mfano umepatiwa the number of turns, you have been given the number of turns in that coil, then we can find that the EMF generated is negative n times the change in flux. We have already seen these symbols. The flux tunaipatia kama phi. So if you're given a coil and you have been given the number of turns, then the EMF induced in that coil will be given by negative n. The negative here implies the length is low. Mali ambapo tunasema that the EMF produced is in the opposite direction, ama it is opposing the current, I mean the change in current, ama the change causing that EMF. So the negative just indicates that EMF produced is opposing. So now you can also find EMF if you are given the value of inductance. Kama uko na value ya inductance L, then and you have current, this is current I. So you'll take that the value of EMF is the value of inductance times the change in current in that circuit or in that conductor. So remember we are saying that inductance can be brought about by the generated EMF can be brought about by the change in flux, ama the magnetic field, or the change in current. The change in current generates the change in magnetic field, which induces an EMF. So we can find the EMF by calculating it by the change in flux, and we can find the EMF produced by calculating the by using the change in current. Now L is the value of inductance, and we have the unit of inductance is henries. So let us try this example. We have been told that we determine the EMF induced in a coil of 200 turns. We'll calculate the EMF of a coil which has 200 turns, where there is a change of flux. The change of flux is 25 milliweber. Please note, I want us to remember these units to see this how the change in flux is 25 milliweber, and the change in time is 50 milliseconds. Na tumeambiwa tutafute the EMF induced. Now which formula will we use between those two ambazo tumefanya? Hizo ambazo nimeonyesha hapo. We will use the first one because we have the number of turns, and we have the number of turns. So we will take So we will take the formula E is equals to negative N, change of flux with respect to time. This is equals to negative 200 multiplied by the change in flux is 25 milliweber. So we have to change this from milli to Weber. And how do we do that? Okay? We divide by 1,000.
10 power negative 3 multiplied by
10 power negative 3, yes. Over the change in time. And the change in time is in 50 milliseconds. So we also have to change the 50 milliseconds to seconds. And we do the same. We divide by 1,000, now we multiply by 10 raised to power negative 3. So what will be the value of our induced voltage? Take 25 times 10 raised to power negative 3 divided by 50 times 10 raised to power negative 3 times negative 100. No, negative 200, I mean. Divided times negative 200. You get that the induced voltage in our circuit in our conductor is 100 volts. This negative just indicates that it is opposing the direction. It is opposing the change, what is causing the induction, which is the change in current or the change in flux. Now let's try this. We have a flux of 400. A flux of 400. Let me project it. Shule luko na sisi?
Yes.
Okay. Now, we've been told that a flux of 400 microweber passes through a 150 turn coil. A flux of passing through a 150 turn coil is reversed in 40 milliseconds. So find the average EMF induced. I'll give you a minute to write down that question. Tumeandika?
Yes.
Now, how we will do it? Tumeambia that our flux is reversing, so it will so microweber, and the change in time is 40 milliseconds. Now we've been told that this flux is reversing as it passes the 150 turn coil, which is 150. It is reversing. That means that itatoka from positive 400 microweber ifike mpaka negative 400 microweber. So the total change in flux will be 400 plus 400. Sawa. The total flux in this case will therefore be 800 microweber. Kwa mfano, when we talk about kama hii, we have an alternating voltage ama current. When I ask you to find the peak to peak voltage, it is the ama current. It will be from this point to this point. Remember that this is the positive side and this is the negative side. Let us take this example. Kwa mfano, our flux ime reverse from the positive 400 ikafika mpaka positive negative 400. So what will be hii yote, the total? It will be this 400 minus 400, which becomes a total of 800. Are we together there?
Yes.
So therefore, our induced voltage will be negative N change in flux over change in time. Our N is negative 150. Times our change in flux, our total change in flux will be 800 times. Remember now it is micro. It is 800 microweber, which is now 10 raised to power negative 6. Over change in time, 40 milliseconds. When you change it to seconds, itakuwa 40 times 10 raised to power negative 3. I want you to see the difference between micro and milli. Therefore, this gives us the EMF induced in that conductor will be negative 150 times 800 times 10 raised to power negative 6 divided by 40 times 10 raised to negative 3. That gives you an average EMF, induced EMF of 3 volts. Sawa.
Yes.
Is there a question up to that point? Now let us try this example. I will dictate it because since I don't have it in my presentation. We have been told to calculate the EMF induced. Calculate the EMF induced in a coil of inductance. Calculate the EMF induced in a coil of inductance 12 Henry. Calculate the EMF induced in a conductor in a coil of inductance 12 Henry by a current changing at the rate of 4 amperes per second. Calculate the EMF induced in a coil of inductance 12 Henry by a current changing at the rate of 4 amperes per second. Now we will use the second tutatumia the second formula ambayo ilikuwa the induced EMF will be given by the inductance, remember always to put a negative, multiply by the change in current over the change in time. Now we have been given the value of inductance is L is 12 Henry. The change in current over the change in time, dI over dt is 4 amperes per second. So the EMF induced will therefore be negative 12 times 4. Remember now you don't have, you've already been given the change in current over the change in time. So our EMF induced will therefore be minus 12 times 4 inakupatia minus 48 volts. Do you have a question?
So we have already combined the change in current
Yes.
with the change in time.
Yes. As per that question, they have already given you the change in current or the change in time. Yes, how? Okay. Now, I had mentioned that we have these components in a circuit that increase inductance, and they're called inductors. Sawa. Now, these inductance operate on the principle that once that magnetic field is created around a conductor, once you have that magnetic field created in a conductor, then energy will be stored in that field. Sawa. what happens is when you energize that circuit and there is an inductor stored, then a magnetic field will be formed around that inductor. Vile tumekuwa tukisema, you'll have change in current. That change in current will generate an EMF, will generate a magnetic field. That magnetic field will now induce an EMF. Now that magnetic field formed around that inductor stores energy. So when you energize that circuit, then it stores energy. When you close that circuit, when you open that circuit, then that energy is released. Are we together? Kwa mfano, a very good example ni ukiswitch on your switch. Kuna ile spark ambayo inatoanga ukiwasha socket ama switch. That is that energy that has been stored by the magnetic field around an inductor ama around a coil being released. Now we can calculate that value of that energy stored by saying that it is equals to a half the value times L times I. By now we should know what L and I mean. Tunaelewa? We do understand what L and I mean. LB is the value of inductance in henries and I is the current in amperes. Now, what are some of the factors that affect the inductance? When you have an inductor in a circuit, what will be some of the factors that will increase or decrease the inductance? Number one, the number of turns. When you have a number of turns in that inductor, then if there are more, the higher the number, then the more the inductance in, the higher the inductance in that circuit. Okay? The cross-sectional area of the coil used in that conductor, in that inductor. So the greater that area, the cross-sectional area, then the higher the inductance. Are we together? Remember, the principle of inductance is that you have a coil wrapped, a coil, then it is energized. You connect it to a power source. This is essentially an electromagnet. So if that magnet, that coil has a core inside it, kwa mfano, you can make, I don't know if you have ever done this experiment ukiwa primary ama high school, ukachukua a nail, kisha ukachukua a copper wire ukaifunga around that nail. Then you connect that to a battery. What you have there is an electromagnet. Now the strength of that magnet can be increased by putting a core. Hiyo msumari hapo katikati ya hiyo coil. So if you have a core within a coil of an inductor, then the inductance is increased because you are setting a concentrated magnetic field. If you don't have a core, you will still have a magnetic field, but itakuwa weak. Are we together? Tuko sawa?
So the core is the nail.
The nail now. Kama transformer. Have you ever seen a transformer?
Yes.
Kuna ile ujaona vile inakaa ndani. Let me see if I have one, a small one. If I do, niwaonyeshe vile inakaa.
Kitu kama radio ama
Hizo zote.
they are the same.
They are the same. The difference ni size tu. Si unaona vile hiyo wire imekuwa wound around, imezungushwa around a core. So that core it will increase the magnetic field.
Yes.
Because it is a ferromagnetic material, ni kitu ambayo will induce more magnetism. Now, tumesema that the energy calculated will be given by a half Li squared. Now let us try an example ambayo nimeproject hapo. Sorry. You're told that an 8 Henry inductor has a current of 3 amperes flowing through it. Now, how much energy is stored in the magnetic field of the inductor? How much magnetic field is stored in the inductor? Tumeandika. Give me an answer. That should be straightforward kwa sababu formula ni a half Li squared. Yes. The unit of measurement for energy is joules. Cheryl, are we together?
No.
Yeah. Umepata 36 pia?
Sijapata.
Unafanya kweli ama bado? Ama unasikiza tu? When you take a half Li squared, and then you replace the L, the value of L and I, what do you get? Let us do it together. We are told that the work, the energy stored in the magnetic field of an inductor is given by a half Li squared, where this L is the value of inductance in henries and I is the current in amperes. Now we've been told that the value of the inductance is 8 henries. And the value of current in flowing through that inductor is 3 amperes. So what will be the energy stored in that magnetic field produced by the inductor? Itakuwa a half times L. L, the value is 8 henries, times the value of the current flowing through that inductor, which is 3 amperes. Okay? But you square that value of current. So what do you get? 36 joules. Joules is the unit of measurement for energy. Sawa?
Yes.
Now, we can also be able to calculate the inductance of a coil. If you don't have an inductor in your circuit, then it is also possible to calculate the value of inductance in a coil. Remember, a coil will also have that property of inductance kwa sababu that coil will generate a magnetic field which induces EMF, whether it is mutual or whether it is self. So the value of the inductance in a coil will be given by N, which is the number of turns, the number of turns in that coil, multiplied by the flux, the magnetic flux over the current flowing in that coil. Are we together?
Yes.
Now let us try this example. You have a coil which has 4 amperes flowing through it, and that coil has 800 turns. Imezungushwa 800 times with a flux, a magnetic flux of 5 milliweber. So what will be the inductance in that coil? The value of inductance in that coil? One hand. Cheryl?
Yes.
Okay.
1.
Umepata 1?
Yes.
Okay. Now let us, I don't know if Let me see. Yes. Let us try that one. We are given three questions. You're told that a flux of 25 milliweber links with a 15-turn coil when a current of 3 ampere passes through the coil. You're told calculate the inductance of that coil, calculate the energy stored in that magnetic field, and calculate the average EMF induced if the current falls to 0 in 15 milliseconds, on 50 milliseconds. So I'll give you a minute to write that question, then we'll do it together. Umeandika swali?
Yes.
Okay. Now you're told that a coil, a flux of 25 milliweber links with a 1500 turn coil when a current of 3 amperes passes through the coil. You're told calculate the inductance in that coil. Now, how do we find inductance in a coil? L is given by the flux linking to the coil times the number of turns over the current passing through that coil. Hiyo formula ambayo tumefanya just before. Now, flux in this case is 25 milliweber. When you change that to Weber, then it will be divided by 1000 times 10 raised to power -3. Multiplied by the number of turns, which is 1500 turns in that coil, divided by the current. So what is the value of the inductance in that coil? So 1500 times 25 times 10 raised to power -3 divided by 3. No, ama ni ngapi? Yes, 3.
12.5.
It is 12.5, Benjamin.
Yes.
12.5 Henry. Sawa sawa.
Yes.
The energy stored. How will we find the energy stored in that magnetic field? Energy stored is given by a half times the inductance times the current squared. Now, a half times the value of L. The value of inductance in this case was 12.5 Henry times the value of current, which is 3 squared. So what do we get? 0.5 times 12.5 times 3 squared. We get that the energy stored in the magnetic field is 56.25 joules. Okay. Now, the induced EMF. The induced EMF in that coil will be given by, remember now we have been given the inductance. We've been given the inductance, so we can use this formula, negative L, change in current over change in time. Change in current over change in time. Now, we are told, if you look at the question was saying that the third question, the average EMF induced in the current, the average EMF induced if the current falls to 0. Now, the change in current will be 3 minus 0. Like it is inatoka from 3 mpaka 0. So the change will be 3 minus 0. And the change in time will be 150 milliseconds. Are we together? The change in time is 3. The change in current is 3 minus 0, and the change in time is 150 milliseconds. Therefore, the induced EMF will be minus L. Our inductance, we got it as 12.5, multiplied by the change in current, which is 3 minus 0, divided by the time, the change in time, which is 150 milliseconds. This gives us an induced EMF of, this will give us an induced EMF of 12.5 times 3 over 150 inakupatia nini? Minus 250 volts. Is there a question up to there? Kuna swali? Now, let me see if I have this question with me. Let me see if it's the same one. Let me project a question. Let us write down that example and we calculate it together. Tumeandika?
Just a minute.
Okay. Cheryl, uko sawa pia?
Yes.
Now, attempt that question first before I do it. Niambia kama utapata answer. What will be the value of the inductance? Umepata answer ni ngapi?
Calculate the flux link
Flux.
further.
Oh, the flux. What will be the value of the flux? Yeah.
8 times
Flux
4.
is 12 milliwaba. 12 milliwaba.
Cheryl, umepata ngapi?
8 times 10 is
No, umepata answer ni 8 times 10 raised to power negative 3, but the value is Weber. So, not milliweber. If you want to change now to milliweber, you multiply by 1,000 to get 8 milliweber. Benjamin, it is 8.
It is 8.
Yes, 8.
And somewhere.
Remember that we get the inductance as the number of turns times the flux divided by the current. Now, if you get the flux, if you make the flux the subject, then itakuwa the inductance times the current divided by the number of turns. We have the value of inductance as 3 Henry. We have the value of current as 2. And we have
Also,
the...
I used the wrong figure instead of 2. I used 3.
Oh, it is 2.
That's why. Yes.
So napata that the flux is 8 times 10 raised to power negative 3 Weber or 8 milliweber. Now what will be the value of the induced EMF? Napata that the value of flux. No. Now what will be the value of induced EMF?
if you say 3.
Yes? Negative? What? Negative 0.3 what?
Volts.
The answer is negative, but tumekosea. Kuna mahali angalia vizuri sana hapo. You can get the EMF induced as negative L, change in current or change in time, or that. We can use either of these to get the answer. So if you're using the first one, then you use the inductance and the current. If you're using the second one, then use the number of turns and the flux, the change in flux. Unapata answer ni ngapi?
I got negative 450. I don't know if but I used the...
Let us use the first one. Tumia ya kwanza. The EMF induced will be given by the inductance times the change in current with respect to time. Now, the value of inductance is 3 Henry, multiplied by the change in current over the change in time. Now, we are being told that the current is falling from 2 to 0.
To 0.
So the change in current will be from 2 to 0.
0.
In a time of 20
20.
milliseconds. Now, when you change milliseconds to seconds, inakuwa times 10 raised to power negative 3. Ama divided by 1,000. So, 2 divided by 20 times 10 raised to negative 3. Then you multiply that by negative 3. The inductance. You get that the induced EMF will be negative 300 volts.
10.
Oh, negative 300.
Are you together?
Yes.
Tutumie hiyo ya pili basi ndio tuone kama tumeelewa. The induced EMF is given by the number of turns in that coil. And the number of turns in our coil is 750. So negative 750 multiplied by the change in flux. Our change in flux we've tulipata as 8 milliweber, which is 8 times 10 raised to power negative 3 Weber, divided by the change in time. And our change in time is 20 milliseconds, or 20 times 10 raised to power negative 3 seconds. We should get the same answer. So 8 times 10 raised to power negative 3 divided by 20 times 10 raised to power negative 3 times L times the number of turns, and now you include the negative to show direction. So you find that the answer is negative 300 as well. Negative 300 volts. So,
Yes.
any question? Kuna swali? Let's try this example. I don't have it projected in my presentation, so I will just dictate it to you. So write it down mahali. No, we have already done it. We have done it already. You shall find. Now, I want to talk about something something small. We had said that inductance can be self-inductance or it can be mutual inductance. When we talk about self-inductance, we say that the change in current in that conductor or in that circuit will cause EMF. Are you together? Will cause the change in current in that circuit will cause a change in the magnetic field, and that change in magnetic field will induce an EMF. When that EMF is induced in the same conductor or in the same circuit, then that is known as self-inductance. Now, when you have a change in current which causes a change in the magnetic field, which induces EMF in one coil, kwa mfano, let's say this is a transformer. We have the primary coil here and we have the secondary coil. Now, when you have an induced EMF, the change in current in this coil, causing a magnetic field which induces an EMF in this coil, which in turn induces EMF or voltage in the second coil, then this is known as mutual inductance. Are you together? Now, mutual inductance ni kwamba uko na steam, you have a current passing through this coil. Now, that change in current in this primary coil, kwa mfano, will cause a magnetic field, a change in magnetic field. Remember, when current flows through a conductor, a magnetic field is formed around that conductor. So when that current changes in value, then the magnetic field around that conductor will also change. So that change in the magnetic field, the change in current, will induce an EMF, a voltage in the conductor. So you can be able to calculate the voltage between the two ends of the coil. Now, this EMF induced in this coil can induce another EMF in a circuit or in a coil that is near. Kwa sababu this conductor, remember that we'll have a magnetic field around this. So when this circuit this coil interacts with the induced EMF the magnetic field from the first coil, then another EMF will be induced in this second coil, and that is what we call mutual inductance. Sawa?
Yes.
This is the principle that transformers work. We use the principle of the way of transformers work. They work on the principle of mutual inductance. Now, we can be able to calculate the EMF in the second coil. The adjacent coil, we can be able to calculate the EMF, and it is given by the subscript 2 and the subscript 1. These are referring to the second and the first coil. So for 2, this is the second coil, and for 1, this is the first coil. So the EMF induced in the second coil will be given by the inductance multiplied by, this is inductance, inductance multiplied by the change in current in the first coil with respect to time. Are you together? Now let's do this example. We are told to calculate calculate the mutual inductance. Calculate the mutual inductance between two coils. Calculate the mutual inductance between two coils when a current changing at 200 amperes per second in one coil induces an EMF of 1.5 volts in the other coil. Calculate the mutual inductance. This M is just to differentiate between the mutual inductance and ile nyingine ambayo tulikuwa tumesema L. They're all the same, but this now refers to mutual inductance. When you talk about self-inductance, sana we'll be using L to denote it. Now we're told calculate the mutual inductance between two coils when a current changing at 200 amperes in one coil induces an EMF of 1.5 volts in the other coil. Now, the EMF induced, I'll put this. This means modulus. Modulus just means that we are taking the actual value, the absolute value. So we do away with the negative part. So this will be given by the mutual inductance multiplied by the change in current over the change in time, the change in current in the first coil. Now, we are told that the EMF induced in the second coil is 1.5. So what will be the value of the mutual inductance? And the change in current is 200 amperes. So the change in current with respect to time is 200 amperes per second. So the mutual inductance will therefore be 1.5 divided by 200. 1.5 divided by 200, giving you that the mutual inductance is
7.5 times 10 raised.
7.5 times 10 raised to power negative 3 Henry. Sawa.
Okay.
Sawa. Now, inaonekana tumepotea kidogo. Kuna swali?
So which means our E2 is 1.5.
Yes, we have been told the change in current in one coil. Let's say this, we have two coils here. This is our first coil and this is our second coil. The current in the first coil is changing at 200 amperes per second. This change in the current with respect to time is inducing an EMF of 1.5 volts in the other coil. So what will be the mutual inductance between these two coils? Remember, the formula is given by E2, the EMF induced in the second coil is given by the mutual inductance multiplied by the change in current in the first coil with respect to time. We have already been given the change in current with respect to time as 200 amperes per second. We've been told that the 1.5 volts is induced in the second current, so we already have that 1.5. So what we are looking for now is the mutual inductance. So the mutual inductance will be 1.5 divided by 200, giving you the answer of 7.5 times 10 raised to power negative 3 Henry. So.
Yes.
Let's try the last example for today. We are told that the mutual inductance, between two coils is 18 millihenry. Calculate the steady rate of change of current in one coil to induce an EMF of 0.72 volts in the other coil. The mutual inductance between two coils is 18 millihenry. Calculate the steady rate of change of current in one coil to induce an EMF of 0.72 volts in the other coil. What does this mean? The formula still remains the same. Change in current in the first coil with respect to time. So the induced EMF in the second coil is given by the mutual inductance times the change in current in one coil with respect to time. We have already been given the induced EMF in the second coil, which is 0.72 volts. So 0.72 volts will be given by the mutual inductance. We have been told that the mutual inductance between the two coils is 18 millihenry. So when we change 18 millihenry to henry, then we multiply it by the 10 raised to the power negative 3. Now, this is what you're being told to find. What will be the rate of change of current with respect to time? DAE1 over dt. So the change of current in one coil with respect to time will be given by this 0.72 divided by 0.018 or 18 times 10 raised to the power negative 3. So 0.72 divided by 0.018. This gives you that the change of current with respect to time is 40 amperes per second. Are we together?
Yes.
Now for today tulikuwa tufanya tu mambo ya inductance, calculations on inductance, the energy stored by the magnetic fields, and so that we can finish up with this topic. Really tuende the next topic. So what I'll do this week is I will send an assignment in Google Classroom on this topic, magnetism and electromagnetism, which we'll submit next week, so that on Friday we can start on something else.